Optical imaging is a non-invasive imaging technique that utilizes visible, ultraviolet, and infrared light waves, which allow us significant insight into various types of samples. An optical microscope is an imaging instrument that utilizes visible light waves to illuminate a sample which sits on the stage just below the objective, a small lens that brings the image of the sample into focus at a short distance. The image is acquired similar to the way a camera takes a picture, meaning the whole field of view is recorded at once onto a grid of pixels. The physics of an optical microscope is important because there is one focal plane, which is where you want to image, but the issue is that the light used to illuminate the sample creates many focal planes and results in an out-of-focus image. In a perfect system, if you image a one-point input, the imaging system should ideally generate an image of an identical point. Of course, this perfect system does not exist, and the blur that you see in an imperfect image is the response of the imaging system to the one-point input, which is called the point spread function. This is useful for determining the resolution performance of different objectives and imaging systems. The reason this does not and cannot exist is due to the diffraction limit, a fundamental concept in physics that cannot be defied. In 1873, the German physicist Ernst Abbe was credited for discovering the resolution limit of the microscope. He found that microscopes, telescopes, and other optical imaging instruments are fundamentally limited by the diffraction of light. This is currently defined by the Abbe limit. The numerical aperture is ultimately the field of view of the lens, but more specifically is the measure of the number of highly diffracted image-forming light rays captured by the objective. Numerical aperture is dependent on the angular aperture, which is the maximum angle of image-forming light rays diffracted by the sample that the front lens can capture when the sample is focused, or the angle between the microscope's optical axis and the direction of the most oblique light rays. It is common to decrease the focal length or use an immersion medium such as water, glycerin, or immersion oil to increase the numerical aperture, which will in turn generate a more highly resolved image. In 1957, Marvin Minsky patented the first double-focusing confocal scanning microscope, which included 2 lenses and 2 pinholes. Since the power of resolution of the microscope depends upon the degree to which a geometric point can be approximated, the first screening device was imperative to produce light from a point source. The objective, or the first lens, focused the light emanating from the first pinhole upon the sample to produce an illuminated point. The second lens focused the illuminated sample point upon the second pinhole, which in turn only allowed the most focused light to pass through to the detector. Minsky's design didn't attract an extravagant amount of attention. It wasn't until later, around 1960, when the laser was invented, that new designs incorporated a laser illumination system, which minimized the need for excitation filters and produced a very bright and tightly focused beam of light. Minsky built a confocal microscope with 2 objective lenses, but modern confocal laser scanning microscopes are designed with a laser as the light source and only 1 objective lens operated in reflected light mode. The laser emits the excitation light, which is partially transmitted through and partially reflected off of the beam splitter, which is simply 2 triangular glass prisms with a resin layer in between. The role of the objective is to focus the excitation light onto a focal plane in order to ensure constructive interference of the focused wavefront at the sample plane. Let's say you are imaging a cell that is approximately 5 to 20 micrometers using a laser that is only a few hundred nanometers, so the illumination point is thousands of times smaller than the sample. There are 2 options to obtain images of all the points within the sample. First, physically move the sample stage as Minsky did, or second, using motorized mirrors, move the laser across the sample to scan the entire area. The second option is much easier to do and is termed Raster Scanning. Since the laser is scanned, the collection of light has to be different and cannot use a camera. The laser moves pixel by pixel and light is collected at each pixel using a photomultiplier tube which collects photons and amplifies the signal, which creates a digital signal that can be processed by a computer to generate the whole image. Another way to operate a confocal microscope is in fluorescence mode. The difference is that once the excitation light reaches the sample, another wavelength is generated and the excitation light is reflected back by the dichroic filter and only the emitted light is transmitted through to the pinhole and detector. In fluorescence mode, you don't want to image the excitation light because it is stronger and will dominate the image. Therefore, you only want to image the emitted light because that is what will show the fluorescing sample. One of the great advantages to confocal microscopy is that you can control the depth of field, which is also called the depth or Z resolution, to create optical sections of thick samples without losing image quality. The illumination is achieved by non-invasively scanning 1 or more focused beams of light across the sample, rather than sectioning using physical means, which would likely destroy the sample. This allows for the 3D reconstruction of a sample from images captured at different focal planes. Confocal microscopy is most frequently used to image biological samples, but is not limited to the field of biology as it is used in material science, semiconductor inspection, and life science. While confocal microscopy has great advantages, there are some trade-offs. It is time-consuming to raster scan, and the process will take longer depending on the size of the sample. Therefore, you may not be able to image a process that is happening quickly. While you can produce superior quality images, the resolution is still not equivalent to that of an electron microscope. The lenses can have chromatic and spherical aberrations, and you can have artifacts if the imaging is not done properly. This instrument also requires software and a computer to process the raster scanned images. Over the past few years, engineering researchers at the University of Houston have used confocal microscopy to confirm reductions in biofilm thickness when specific bacteria were exposed to heavy metals, examine site-specific adsorption of various growth inhibitors to crystal surfaces, and examine the attachment of bacteria on glass surfaces during flow through a linear channel. In the mathematics department, researchers have been developing highly efficient automated analysis and processing tools to limit or remove the need for manual quantification and analysis. Researchers at Rice University have been engineering new designs for improved testing and analysis of diseases, from high-resolution microendoscopes to gadolinium conjugated gold nanoshells. The researchers compare results from their novel designs to those obtained using confocal means. As Isaac Asimov once said, "Science can amuse and fascinate us all, but it is engineering that changes the world."